Thanks for the introduction and thanks for the opportunity to talk today. I want to give a little bit of background of this talk, where it came from. I've been wanting to talk about quickest change detection for a little while, but and a colleague had pointed out to me that he knew I worked on quickest change detection, but he hadn't seen me give a talk. But when I started to prepare for this talk, I found that I had 4 half-written talks, and I didn't really like any of the talks. And so I've made, and part of the reason for that is I had several things I wanted to say, and I wasn't sure what sort of audience I was preparing the slides for. So I've made sort of what I call an experimental presentation here, so I hope it goes okay. The stuff I'm going to be talking about today is sort of covers about 10 years worth of work, so I want to acknowledge a lot of people involved in working with me, and I'm going to be talking about stuff that isn't only my work. I'm not sure if Valerie's in the call, but Valerie Ognoski I wanted to acknowledge because more than a decade ago we wrote some papers on what happens when the filter, there's errors in the model being used in a filter. In some sense this is a continuation of that journey. And also Dragan Nesic as well. There is a paper in one of these slides that I wrote with him, and he also introduced me to a stability concept which was important in the main proof I'm going to talk about later in the paper. So I just want to acknowledge that. And most of the work here is to do with stuff I did more recently with my colleagues Jasmine Martin, Tim Malloy. And I acknowledge some various funding sources as well for this work. So as I said, this is a talk in sort of 3 parts, or I don't think I said that, but I'm now saying there is a talk in 3 parts. I'm first going to talk about some engineering applications where you might see the quickest change detection problem emerge. And then I'm going to talk in the middle part of the talk about a specific problem. I'm going to make it sort of concrete, what I'm talking about. And then the last part of the talk, I'm going to go technically a bit deeper and talk about what we recently discovered. I've tried to minimize the amount of maths here to try to make it as accessible to the audience as possible, but there is some maths in the last half of the presentation a little bit. So here's a slide with lots of words on it. This is a description of what is the quickest change detection problem. The most important piece of information probably down, oops, didn't mean to go forward, probably down here. We're talking about a situation where we're sequentially observing data coming, a random data or statistically varying data. And initially it has a probability density B1, and at some point it changes to a density B2. And we're sequentially watching the data, and we want to declare an alert as soon as possible while somehow managing the false alarm rate or some other metric of false alarms. And this is an important problem in a wide ranging of engineering situations where you're monitoring a process and want to see when it breaks or its behavior changes, and you'd like to automatically alert that's going to happen. So this is a problem we're going to be talking about today in this talk. Here's a visual representation of this sort of problem and what we're talking about. So we're sequentially observing a process, we're going along here, at some point the statistical properties of the process change, and we would like to declare that that has happened, declare an alert, and we'd like to do that as soon as possible, whilst not being overly aggressive and having too many false alarms in the way we do this. So here's a little toy problem to further stress this out, stretch the concept out for you a little bit, and I've generated some random data in MATLAB, and at time point 5000, statistics change from a 0 mean univariate Gaussian to a univariate Gaussian with mean 1. And I've changed the color to make it easier for you to see, but you could probably sort of see that by eyeballing it. And the sort of problem we're interested here in is we're sequentially watching this data, and we want to declare when the change has happened. And whilst it's easy sort of to see with your eyeball, we want an algorithm to do that. And it's not like you could sort of say, or as soon as we get a piece of data above 2, I'm going to say a change has happened. All right. However, there are a range of techniques for doing this, and I'll plot here down the bottom right a test statistic called QSUM, relatively well known, and you can see after time point 5000, the statistics consistently grows. So the idea is that you could set a threshold value that you're going to check, let's say 100, and then if this test statistic gets above 100, you declare an alert. And from the look at this data here, you wouldn't get many false alarms, but of course this is synthetically generated data. Okay, so now I'm going to talk about a range of applications, and I've worked in a lot of sort of aerospace problems, so these applications will be biased towards aerospace, but hopefully you can match these to your own engineering domains and application domains and sort of get an idea. So recently I've had about 3 fourth-year students doing capstone projects, looking at this data set. This is data set where some flights were taken, some flights without faults, and some flights where there were faults. And the faults here are things like an engine failure or an aileron failure. And if you think about, well, my bigger picture context is I'm trying to build resilient robotic or platform sort of systems. You might want systems that can detect when they've had a fault or experienced a fault and then change their behaviours, like a return to home or something like that. So this data has all sorts of different sort of things that you can get from avionics systems, INS measurements, inertial measurements, things like that. And the task of students with sort of working out what sort of fault detection techniques work, what sort of signals are the easiest to detect different sorts of faults. This is another application I looked at with a PhD student, Justin Kennedy. In this situation, this is a maritime situation. There's this phenomena called parametric roll resonance, where if the wave encounter frequency is a certain zone, then there's a roll oscillation that grows, amplitude grows without limit, and that is dangerous. If you can imagine a cargo ship tipping over and perhaps cargo falling off the boat. So here's a picture of some data. So we have data from a roll, and this is sort of the amplitude oscillation that effect you're trying to detect. In this paper, we didn't use quickest change detection techniques. We used another sort of detector, but we're aware that it's the sort of problem that you could use quickest change detection techniques for. Here's 2 more applications. Again, you're seeing my aerospace background here. So in this problem here, we're trying to detect when an aircraft's heading might change. And why this might be important is, say you're operating in national airspace and you've detected other aircraft and you've reached a point where you feel safe that you're not on a collision course. However, an aircraft changes its heading. You might want an alert so that you can go back and now reevaluate whether things are still safe. I've looked at doing this a couple of different ways. So with Troy Bruggeman, we looked at it, somehow we had access to heading information directly from the platform when we looked at quickest change detection off that information. And with Kim, we looked at how you might use measurement information from an image sensor to detect when the heading of the aircraft changed. Now I'm going to talk about a problem that I've spent more than 10 years of my life looking at, a long time, and it sucked up a lot of effort. It's a challenging detection problem. And this is the problem that probably inspired our interest in quickest change detection problems. The basics of this application is that for unmanned aerial systems or vehicles to have improved access to the national airspace, there's an argument that they need to have some system that replicates the human pilot eyes. In national airspace, a human pilot's eyeball is the last line of defence for possible mid-air collision, and unmanned aerial systems obviously don't have a human on board. And so part of the argument goes that a vision sensor is a reasonable proxy for a human pilot's vision system. And additionally, for the class of platforms we're looking at, to the best of my knowledge, it's not quite possible for them to carry a radar sensor. I think that's still a technically correct statement. They haven't quite got radar sensors suitable for this class of platforms. So the basic idea as a quickest change detection problem is that in this problem here, the whole image is measurement. If in the previous examples gave the idea that we were detecting on scalar signals, here we have a whole image. It's the signal of interest, and we have some description of it before, when there's no aircraft present, what its statistics are, and a description of what those statistics might be afterwards. And here's an example of the imagery from the sort of distances you need to detect. It's sort of implied you need to detect about 12.5 seconds before closest approach, and in the class of aircraft we're working with, that's more than 2 kilometres away, and the aircraft will look something like this. And this is what I would call a low SNR sort of problem. So in addition to having these 2 sorts of densities, we supplement or amplify the difference between these signals using a hidden Markov model, which is used to model the temporal characteristics of the aircraft, in the sense that an aircraft is expected to persist over multiple frames in roughly the same location, and we use that extra information to amplify the statistic. I'll talk a little bit more about this application a little bit later. Here's some more, or one more slide on this anyway before I go to another topic matter. This is sort of what you can imagine happening. So we have a test statistic here, it's going along, and we have a threshold, which we're going to use to declare an aircraft present whenever, if we go across this threshold. And then at this point here, it crosses, and this is when the aircraft actually is in the field of view. It drops down afterwards because this was a physical experiment and the aircraft actually passed the sensor aircraft. I guess it's interesting that we got to fly two aircraft at each other in near collision course geometry. This point here corresponds to a cloud artifact that looks something like an aircraft. It started to confuse the detector, but not enough that you would it declares an alert. And so this is basically the sort of pictures I've been looking at for 10 years, trying to make the aircraft detection part higher and reduce these things here so that we get better detection performance in terms of the trade-off between detection range and false alarm. So this is more recent work. So more recently, we've reached the point where, so up until before recently, we had our detection system had a bit of a hack and the theory didn't sort of knit together properly or fully. More recently, in 2017 to 2019, my colleagues Jasmine Martin and Kim Malloy, we've sort of developed a new detector, and so we have nice theory that connects the whole thing together as a nice theoretical argument, and with theory and detector that matches the physical situation better. We're not only interested in theory, having good theory, we're actually engineers as well, and so we now have even better performance, and we have detection range greater than 2.3 kilometres with very low SNR, in very low SNR detection environment, with very low false alarm rates, and potentially exceeding human level performance, which is a great place to reach after such a long journey. These are the sort of pictures we generate to characterise our system. Hopefully on the previous slide, you got the idea that if you move that threshold up and down, if you moved it down, you might get early detection, but you might also increase false alarm rates, and up later detection, but less false alarm rates. We sort of describe that in these sort of curves here, where along the x-axis is false alarms, and up the y-axis is mean detection range, and the red line here is better, represents a better system performance because it's higher than the blue line. And although we were only really interested in operating the system down here, because if they kept on throwing too many false alarms, the human user is just going to turn it off, right? We do characterise this sort of whole curve here. All right, so here I want to paint a landscape or a canvas of fault detection and change detection approaches. So the first one is, there may be some people in this Zoom call that have heard of this or used it or applied it. It's what I call a fault detection type approach. And the vanilla version of this is you have a filter, let's say a Karma filter, and you run it, and you build a model and you run it, and you do a chi-square test on the filter residue. And as the filter residue starts looking wonky and the statistics are a bit weird, then you say a fault has occurred. There are other forms of how you could do fault detection in this class of techniques. The next more sophisticated technique is what I call classical Bayesian quickest change detection, and it's got a non-ergodic Bayesian change model. And what that word means and why that's significant, I'll talk a little bit more about later. And its test rule is really a test on the no change posterior. The next level of sophistication might be something like intermediate signal detector, which is our detector that we posted in the last 3 years, and it's got an ergodic Bayesian change detection model, or ergodic change model, which again, I'll explain what that means a little bit more later. And its test is also a test on the signal posterior. Increasing complexity, you get to something to perhaps like the non-Bayesian quickest change detection, and it has a non-random change event model. And this is a sort of problem that I believe Tim Malloy gave a talk about earlier in the year in this seminar program. And its solution is the famous Q-sum test. So there may also be people in this call who've heard of the Q-sum test. It's quite well known. And in fact, the test I showed earlier in my toy problem. And these are, you can have vanilla versions of these problems, and then you can also have robust versions of these problems with minimax type criteria where you say something about the before and after change models being in sets or something like that. Okay, what technique would you use in different circumstances? I tried to describe this in this table where we have the rows being changing S&R, signal noise ratio, and columns being more or less information that you know about the before and after change models, which I've just denoted here as PDFs. And then I've ranked, again, repeated the possible techniques here on the left: fault detection, Bayesian quickest change detection, our ISD, and a non-Bayesian quickest change detection. So this part here of the table is the easiest, and this part here of the table is the hardest. So the takeaway message is if you've sort of got medium to high S&R, probably something like fault detection is enough, and that's probably why it's sort of well known. When you start to have lower and lower S&R, then you need more and more sophisticated techniques. And I guess these two here, Bayesian quickest change detection and non-Bayesian quickest change detection, this is part of the story I'm going to talk about today. These problems over here where you know not too much about the models, perhaps they're not even in a parameterized class of PDFs, they're open problems and they're challenging. At least I don't know how to solve them. All right, so now to the middle part of the talk, and I'm going to now get concrete, a little bit concrete, and I'm going to talk about a very specific problem and make it be precise and write it down in a little bit of detail so we've got something solid to think about. And the problem I chose is Bayesian quickest change detection. Also because it flows into the third part of this talk, but also I quite like this problem because to me it feels like it's at the intersection of optimal control, optimal filtering, and also something in the statistics community. So it's an interesting problem. And the connection between optimal control and optimal filtering is probably sort of not that surprising, and it's known by control theory people. But I don't know the statisticians who are interested in this problem, how much they realise it's connected to this problem. I don't see much in their literature where they're taking advantage of what we know in the control community about, you know, optimal control and dynamic programming and such. So for those interested, Bayesian quickest change detection is an optimal stopping problem. It falls into that class, and optimal stopping problems are an important subclass of optimal control problems. And for those that may not know in a sort of informal sense, their solutions, at least one way of describing these solutions is by discrete time dynamic program equations. And these are rarely have closed form solutions, and they're not necessarily easy objects to work with. So I'm going to state the problem in some detail, and this slide is quite similar to an earlier slide, but I've highlighted the important bit of difference. And this is why this problem is called Bayesian quickest change detection. The Bayesian refers to the model of the change event. So when Tim talked about change detection some time back, he had a different model for the change event. In fact, it was deterministic but unknown. Here we introduce this extra assumption, if you like, that it's a random variable, and we know it's prior. So we're going to look at the problem with the geometric prior, as written there, by that description there. And again, we're looking at the vanilla version of the problem. So we're going to assume before change. At this point, we're looking at the vanilla problem. Before change, it's an IID random variable with a probability density B0, and after the change event, if there is in fact a change event, it's an IID random variable with probability density B1. And from that problem set up, you can introduce and define precisely a thing called P pi and a thing called E pi. So it's okay if you don't want to know about all that. You probably don't need to know about that to get something from this presentation. But it is possible to be very precise here in an information theory sense. Okay, so now what's our criteria for our problem? We're interested in designing a stopping rule. All right, and we want to design this for this stopping rule. Let us define in the Bayesian quickest change detection problem, we're interested in the probability false alarm, and we define it this way, where tau is the stopping rule and nu is the change event. So if we stop before the change event, it's a false alarm, and hence the probability of doing that is the probability false alarm. And we're interested in designing a rule which solves this optimization, this constrained optimization problem, where we want to have the smallest expected delay given subject to a certain constraint on the probability of false alarm. Importantly, for the next slide, is that problem can be rewritten as an unconstrained optimization problem according to this cost function here. All right, so it's running a C times the time since a change event plus the probability of alarm. So C is like a running cost term. It actually corresponds to a Lagrange multiplier in that arises in the process of going from a constrained optimization problem to a non-constrained optimization problem. Okay, so there's a bit of maths on this slide, and so if you don't like your dynamic programming stuff, then that's okay. You can probably still get some value out of the rest of the talk if you don't get what's on this slide. But if you write down a cost function here in terms of different sort of priors that you could have, and for different choices of the stop time, then you can write down where this x hat thing here is the probability of no change event, right, given the measurements. So it's the probability of no change, conditional probability of no change. You can define a value function as the minimum value of that cost. The stopping rule leads to the minimum value of that cost. Sorry, the minimum value of that cost for some over the possible stopping rules you could choose. And it turns out that this value function satisfies this discrete recursion. And I've called it a variational inequality. It's probably stealing words inappropriately because that's what the object is called in a continuous time setting. But I think of it being a similar sort of object, and that's why I'm calling it a variational inequality. And so the way this works is in red, if you can either select the red or the green, and you choose the one which minimises this. So this is like the future cost of keep on operating, and this is the cost of actually stopping at this time point. And so that's the sort of way this recursion sort of works, where this thing here is one step ahead of the sort of filter that's involved in this problem. Now this value function encodes the optimal solution, but as written down, this is sort of challenging to solve recursive directly. The remarkable thing, or perhaps not so remarkable, is that it can be shown that this optimal rule for solving this Bayesian quickest change detection problem can be written as a simple threshold test. So basically, if you can calculate that posterior, you just check whether it's below a threshold or not. Right? And it's sort of cool that that's such a simple solution. It may or may not be surprising depending on how you think about the world. And also very interestingly, this posterior, the no change posterior that you're interested in, can be efficiently computed by simple recursion. And those who know a bit about my history would know I'd probably like to turn everything into a hidden Markov model filter problem if I could. And it turns out I like thinking about this posterior recursion as a simple two-state hidden Markov model filter. This result was originally established in the 1963, so it's an old result. But if you're interested in learning more about quickest change detection and you're coming from a control community, I might recommend Vikram Krishnamurthy's book, 2016 book. It's got a modern, elegant treatment, which I think is probably more accessible to some than the original 1963 paper. All right, it turns out that you can write a convenient recursion for that no change posterior that may or may not surprise you, and you can write it as written at that first equation up here. And I've got little proof steps here, but you encode it as a hidden Markov model. Because the hidden Markov model's only got two states, it turns out that's really just one state, because the two states have to sum to the value of 1, and so you can sort of rewrite these recursions and stuff. Why that is important is that it starts to look like a linear sort of expression, right? And that opens it up for some analysis. So anyone that's worked with hidden Markov model filters, they're a bit difficult to analyze because they're nonlinear, not as easy or nice as trying to understand the stability of the Kalman filter, but that sort of opens it up. And so there, I've got a reference to a 2020 paper where this is established, and you might now expect me to talk more about that paper. But I'm going to take a step back. I'm going to talk about something else for a little while, so I frame how you understand what I'm talking about today. So I'm going to talk about the role of model assumptions. So there's a quote there on the slide from Jenkins. All models are wrong, but some are useful. And I assume many in the the Zoom have heard this one before. So it's sort of like a practical acknowledgement as an engineer that it can build something useful even if it's not a perfect representation. So I'm going to tease that apart a little bit. And here's a big slide with a big claim. Empirical science's basic principle is that knowledge should be extracted from observation. So I don't want to say anything controversial. Hopefully that's not too controversial a claim. I guess there's always room for discussion and debate about that. But the reason for me saying that is that's a sort of way, that's a sort of frame I'm thinking when I talk about what I'm going to talk about next. And I claim one debate is the role of prior knowledge and the models in this process. It's okay if you don't necessarily agree with that statement. I'm not trying to be controversial, but I am trying to frame the way I want to talk about what we discovered. And I'm going to go back a little while and talk about when my interest in this started. So I don't know if there are any PhD students in this call, but be careful what open questions you put in your thesis, because I put an open question in my thesis that pretty much has inspired a research direction for the rest of my career. So perhaps it was a good question, but it's sort of like a question I've struggled to get to understand. And in fact, given the last things I've discovered, I probably feel like I know less about this question than when I wrote it down when I was finishing my PhD. But a good question, I think. Happy I wrote it down. So here's a journey, and I said I might point out a paper I wrote with Dragon. This is a paper up here. So I've been doing following a program of work investigating relative entropy and how it's used to quantify model error. And that's why I alluded to Valery Ogranovsky's contribution to my intellectual thinking on this matter. Probably the first significant step in this was work with Henri in an automatic paper with Dragon in 2017. And I felt at that point, yeah, I had a pretty good answer to that question from my PhD. I could sort of feel now why you could apply hidden Markov models to problems where the things weren't actually discrete states, but they were contiguous states, and how you could do something that was useful. And I could get a feel, we could get a feel for describing the error. Then with Tim Malloy and others wrote a series of papers investigating quickest change detection when there were errors in the models, or when you had lack of information about the models, and it was a decent series of papers. And it had more in it than talking about relative entropy as a description of model error, but it was a good journey. So I felt like we understood some things, but what didn't we know? We reached this point in about 2018. Since 2008, in our vision-based aircraft detection system, we've been using, we're using a HMM to approximate motion, and that's okay. That's one level of approximation. It's discrete, and the aircraft motion is continuous. But we had to introduce this weird model representation where the aircraft, if they left one side of the image, it was expected to return on the opposite side of the image at a pixel side, which is clearly nonsense, right? Clearly an aircraft can't do that. That doesn't make physical sense. However, the detector worked. And so this is a bit weird. And I guess in some sense, the work with Jasmine and Tim Malloy in 2019, we got rid of that problem and we got a better model physically that made sense and made us feel a lot better about the world. But I still didn't have an answer to my question. Like, why didn't Bayesian quickest change detection work in this problem? And so started thinking about that a bit. So what's wrong with Bayesian quickest change detection? There's some old papers. In Bengio in 94.5 showed that RNN and left to right HMMs have difficult temporal modelling because difficulty modelling temporal sort of effects because of vanishing dependence on time. So left to right HMMs, these are HMMs where you can transition through a series of states, but you can't come back. So they sort of only go in one direction. And there's some structural similarity in information flow between left to right HMMs and RNNs. And in the deep learning community or neural net community, RNNs were fixed or replaced by long, short short-term memory type models, and their mixing of information that happens in those sort of networks is somewhat analogous to what happened with or what the information mixes in our ISD detector that we use to fix our problem as well. So there's some cross connection there with the information flow. So further, in the context of HMMs, NGO showed that more structural information helped with learning longer dependencies particularly in low SNR. So we're talking environment where there's really not much strong information. We had observed that Bayesian quick exchange detection didn't seem to work in low SNR, which was our aircraft detection problems. And it turns out that the change event model in Bayesian quick exchange detection is a left to right model. So there's something happening here. So I had this sort of question now coming into my mind. Is there an interplay between low SNR signal environments and left to right models? Right? So at least I had a question to start with. So I'm going to show you the phenomena we discovered before introducing some of the analysis techniques. So the before change model here is the same. The after change models, I'm considering cases of two slightly different after change models. So on the left, we have an after change model, which is m equals 0.23, and on the right is 0.4. And so there's only a slight difference. And again, I've encoded these sequences so that blue is before the change and red is after change. And if you look at those, I don't know I could visually detect the change, but the other thing is I don't know that I could tell the difference between those two data sequences. And I promise they're not the same one. I'm not playing tricks here. There are two different data sequences there. So now, if this was a Bayesian change detection problem, you can build up the posterior test. And so this is what happens with the posterior in these two cases. So looking at the figure on the left, the blue here is the case for 0.4. The red is the 0.23. We have time on this axis here, and we have a log scale here. And so the blue, that's sort of like what I'd normally expect. It's sort of like bounced around. There's no change event. We're only going up to 5,000, so there should be no change being detected here. Sort of bounces around, occasionally gets a couple in a row that make it think a change might have happened, but then it comes back. However, for the case with m equals shift in mean is 0.23, the detector, in this case the posterior, becomes increasingly confident a change has happened in the absence of any change event. Right? So as an engineer, if you thought, oh, I'll need to detect a threshold, where do I set the threshold so this sort of works? Oh, I don't know how you set that threshold to get a meaningful operating system as an engineer. On the right, we did a bit of a Monte Carlo sort of study. We have on the x-axis the difference in mean. On the y-axis, we have the value of the test statistic up to 5,000 steps. We did 1,000 trials. All right. Interestingly, there's an important threshold where the phenomena emerges. So that's pretty neat or pretty interesting phenomena. So, okay. What is the mechanism here? What's going on? All right. So one way of understanding is to think about the special case when the before and after change are the same model. So there's no measurement information. And if you look at the recursions, what will happen is the posterior will be sort of like geometrically decreasing number. All right. So it goes down and down and down and down and down and down. Right. Now just imagine when the before and after change are only slightly different. Right. What is happening is there's only a little bit of measurement information resisting strong pull down of the prior. And so, and then at some point you get just enough that it fractures that going down a bit and it behaves more normally. Right. So as a detector, it has two regions of behavior, and this bad region, I'm calling it, because it's not really useful as an engineer, it has a boundary effect. All right. You can see that all in simulation. We were able to establish some theory and some analysis and describe this. We had to invent some things. We had to invent some new definitions, some new concepts. And this is where I'm thankful to learn some things from Dragan. So we invented this thing, proposed this thing called a weak practical super martingale. I'll explain all these words and why we chose them. The martingale is this, the super martingale is this green bit. So super martingales have these sort of property where they sort of tend to trend down in an conditional expectation sort of sense. The word martingale, my understanding is that's a French word, and it was used in the context of gambling. And so you would have a strategy. That strategy was called a martingale. And you're interested in understanding the properties of martingales, whether they go down or up or in between, because you're interested in what happens to your bank if you're a gambler. So that's that object there. It's weak because it holds in a probabilistic sense, right? And the practical, now this is the way I like to think about a practical stability property is I let you choose this probability here, right? I can go and find an interval such that it holds. So that's that practical, I'm going to call it a practical game tension between us. So whatever thing you choose here for this probability, I can find an interval for which this result holds. All right, so that's the concept. So what it's really saying, we're saying this thing here, which is a log of the no change posterior, is a weak practical super martingale if for any small delta that you choose, I can find a HS such that the no change posterior being close enough to 0, this happens. So I think of this as being like an interval trap, right? And so a weak practical super martingale exists when there's an interval trap such that this bad event happens, right? And so the general idea is it's a probabilistic sort of object. So there's a chance that you'll enter that interval trap and then the bad phenomena will happen. So that's the definition. And so what we're saying is that in the red case, this trap exists, right? And this phenomena happens. In the blue case, no such trap exists, right? And so it's going to behave what you might normally expect. All right, so I don't really like talking too much about proofs, but I'm going to have a go explaining how these, what the key results are, and one of the proofs at least. So one of the important lemmas is this no change posterior update result. And it's sort of saying, so if we write our update in this form here, right, log of the no change posterior the next time step equals this M object plus what was previously, if this log object here, log M of K is negative, then this thing is going down. So essentially I've taken a multiplication recursion and made it into an adaptive looking sort of thing, where we define this M thing as that factor that was in the scalar recursion for the no change posterior update. And so we're going to start looking at the properties of this thing to try and understand when the no change posterior is likely to trend down. So we can establish this bound that again, if you choose that thing, I can find a H delta. If you choose a delta, I can find a H delta such that if the no change posterior is in that little interval, then it satisfies this bound. Right? And where D here is the relative entropy between the no change density and the change density. And the sort of idea is this log minus rho is a negative object. If this thing here is small enough, then the right-hand side is negative, and this thing's going to go down. So that's the sort of strategy being used here and the mechanism involved. So again, recalling this here, I'm going to go through a sketch of the proof to try and give you the idea of the sort of steps. I've restated the lemma result at the top of the slide. The basic strategy is, so N of K is a normalization factor. We do some work to rewrite the log of it or re-express it in this form here. So it looks like minus log of the post-change density plus a little error term. And the important property of this little error term is it can be bounded monotonically by the no change posterior, and hence some sense you can make this as small as you like, and you're sort of making this normalization factor look like something. So then we can re-express our update for M, or recalling it's written like that. So you take the log of that, it's going to be log of NK plus a log of this object here plus a log of B1. So you get your log of 1 minus rho plus this term here. All right, so you're getting the log of the B1 from this factor, and you're getting the minus log of the B2 from this factor here, and you get this object here. All right, and this delta is really some little object you can make bigger than that. All right, and keeping in mind, we can make that thing the smallest, so we can drive that down to whatever size we like by choosing the no change posterior as large as we like. So then you see this, you start to get a bit excited, because those that know how the relative entropy is defined, that looks sort of close. And it turns out with a bit of work, which I'm not going to talk to, you can show that that object there is bounded by the relative entropy. All right, and then because you can make this as small as you like by making the no change posterior as small as like, you get this bound result up here. So that's okay. I'm not going to go into any more detail about that proof. It's a bit tedious. Here's the key result. All right, so you might, I'll go back a slide. You might hope that when this thing is less than this thing, right, in size, right, this thing is going to be negative, and then that's going to lead to the phenomena that you're interested in. And it turns out to be the case, that that's the criteria. It takes a bit of work to show that that's enough. It turns out that if that relative entropy is smaller than that sort of like term there, then the no change posterior is practical weak super martingale as defined previously. I'm going to give a little sketch of the proof, and then I think I've got enough time to talk about the proof in a little bit more detail, because I think it's possible to present this in a presentation and pass some meaning on. So the previous lemma and this above condition means that if you get this thing small enough, the no change posterior will tend to trend down. However, it remains to show that it doesn't escape from that interval trap, that at some future timestamps it doesn't randomly get out of that trap. So that lemma itself is not enough. You could then use a tunneling argument, which allows application of a maximal inequality for positive super martingales. So unfortunately, that object written down naturally, that bound is a super martingale looking object, but it's not positive. It can get negative, and I'm not aware of a maximum inequality for, I'm only aware of maximum inequality for positive super martingales. There are two, we've used one in particular. And the way this sort of goes is you choose for any sort of selected h at delta, then I can choose this auxiliary function, which is a tunnel underneath. At the time we wrote this paper, I hadn't realised that perhaps I could have called this a comparison function. But I've since learned that maybe that's what it should have been called. It then follows, it then stitches together that because we can pick one of these tunneling, these auxiliary objects, and get the result right after for any choice of delta p that you choose, then the argument sticks together and we get a practical stability. All right, so that is the sort of order of the argument it's going to be. I'm actually going to give it a little bit more detail. Hopefully you get something out of this. So noting that we again can write our log of the no change posterior time step k as log of that m object I defined previously plus the log of the previous one. And we can then take expectations, conditional expectations everywhere, and we get this sort of object here. So from the previous lemma, if we have that property, bounding property, then we know this object here is negative, all right? And then we sort of get that we have this sort of thing here, which looks like a super martingale, all right? So we've got that it tends to trend down, but we need to think about, is there a chance for it to jump out of this interval at some future point? Right? So for any delta p you select, there is a h delta such that previous bound holds. All right. Now, imagine selecting smaller objects, hm and hs, and then we define an auxiliary object, and it is related to our no change posterior, but it's a positive super martingale, and it's like a rescaled version of the no change posterior, and it cuts off the last bit of the process when the no change posterior it gets sort of negative, or the part of the auxiliary process, the more scaled process, which would be negative. So it sort of sits a little bit above. It turns out then you can apply maximum inequality for positive super martingales, which directly writes down becomes this sort of statement here. I'm not going to explain in detail, but after a few substitutions, which you can take a little bit of care about, you finish up, and including sort of swapping with the complementary set of this event, you can get this sort of result here. And the key bit is for any delta p greater than 0 you choose, you can choose these parameters. Right? So you can basically choose the right auxiliary process such that that sort of combination of things is less than the delta p you're after, and then they're sort of stitches together, and the main theorem holds. It's basically, visually it looks something like this: is whatever probability you want, I can dive deeper and deeper and deeper past this sort of boundary sort of delta thing. And if I dive down deep enough, then the probability of getting out past delta, H delta, gets smaller and smaller and smaller until I can get the probability down to the probability that you asked for. That's basically the sort of mechanism that goes on here in the proof. All right, when I first told this to a control colleague, they were skeptical, and they said, I know Kalman filters. They didn't say this, I'm being dramatic, but convinced me of the sorcery. And so here's a little thought experiment for you. This is a scalar Kalman filter example. A is the state transition matrix, C is the output mapping matrix. We have a process covariance and a noise covariance. We set these sort of values, and we imagine a sequence. It's a mismatched sequence, but it's got mean 1 and variance. And then imagine what happens as I play around with R. So as I increase R, right, the actual state estimate is going to converge towards 1. And the influence of the measurements is going to decrease and decrease and decrease. The karmic gain is going to go towards 0. And so you can sort of imagine this is what happens for different sorts of R. What I'm saying to you is, if we play this game again, I say you pick the B, then I'm going to be able to find an R such that it gets to that ball and it can't escape. All right, so hopefully you can see the analogy there, and maybe you're willing to make an analogy back to the hidden market model sort of case as well. So the issue is not that the Kalman filter or the HMM filter loses optimality, but the measurements are so weak relative to the model that I wonder if we lose practical observability. I'm sort of thinking, is there another sort of observability concept that we wanted to monitor? Okay, so fixes. So in the quickest change detection problem, there are other quickest change detection approaches that don't suffer the same issues. The behavior really arises because of that left or right non-ergodic model. So there are non-Bayesian techniques, and there are ergodic Bayesian techniques which will work. So the Q-sum algorithm doesn't suffer this phenomena to my knowledge. General thoughts, I would expect similar phenomena to arise in more complex Bayesian quickest change detection problems or other sort of filtering problems involving these left or right models or non-ergodic models with weak observations, and I'm working on another paper at the moment. But my Kalman filter example shows this artifact is also present with ergodic models. So my takeaway message is maybe be careful with models in low SNR situations. I think that's my last slide. So happy to take questions.
Thanks, Jason. It was a very informative talk. So any questions for Jason? Okay. I have a quick question about the minimax criterion the minimax version of these problems that you mentioned.
Yeah.
Where does it come in? What is the worst case that you're trying to? What would the maximum corresponding to?
The minimax is, that's a good question. I haven't thought about the minimax problems for a while, so let me think. So you have sets on the pre-change and the post-change.
Yeah.
I don't have an answer to that question right at the moment because I haven't thought about minimax problems for a couple of years. So
Yeah. Okay.
Yeah, sorry.
No, it's all right. I mean, because I was looking at it. You have the optimal control problem, but I was thinking, what is the max bit of it? Yeah. Okay. Cool.
All right, I might have to send you an email about that.
Yeah, that would be great because that would be good. All right. If there are no other questions, thanks everyone, and thanks Jason for his talk. We won't have a talk next week, but there will be one the week after. Thanks, everyone.
Thanks, everyone. Bye.